Have you ever wanted to use a single button for both power and input for your projects? Some of the most influential designs of all time do exactly that. The iPhone power button not only lets you turn your phone on and off, but lets you take screenshots, access your Apple Wallet, and make emergency phone calls. That's why I created this, the Smart Click Breakout, that enables that for every project. This little thing handles all your power management needs and is smaller than a quarter. This really came about for my e-kayak controller design. I wanted to save space and keep a minimal design, so having a separate button for power and input was off the table. After searching around a bit, that led me to this interesting chip, the PMIC on-off controller. This little guy was exactly what I was looking for. With this IC, the first press of the button wakes the chip up from its deep current-saving sleep and turns on a 3.3 volt output. Any button presses after that act as regular inputs, and a long button press disables the 3.3 volt output, putting the chip back to sleep. This chip is seriously tiny. It's literally smaller than a grain of rice, and that made soldering and prototyping extremely difficult. So that's why I decided to create this PCB breakout so that I can reuse this on future projects and take advantage of the small form factor without the hassle of ever soldering this thing by hand again. Here's a breakdown of my prototyping, testing, and creation of the Smart Click PCB. The goal of this is to drop it into any project going forward and have it handle all my power management needs. So that includes the on-off control, a 3.3 volt rail, and recharging a single cell battery. All the battery circuitry for this board is based off of the Adafruit Feather series. The brains of this breakout is the STM6601 IC. During deep sleep, it draws less than a microamp of current. That means it can run off a single cell LiPo battery for years. I designed the Smart Click to be configurable with a small onboard push button or a set of header pins to install your own external button. The Smart Click can recharge a single cell LiPo battery with a charge current of 100 milliamps and also has a charge indication LED. The battery out pin reports battery voltage through a resistive divider that scales the voltage down for safe reading on a microcontroller. My goal was to make the PCB as small as possible while keeping as many useful features as possible. I placed the smallest components on the back side in order to use a stencil and hot plate. Then all the larger components I put on the front side for hand soldering. Huge thanks to PCBWay. They really helped make this project possible, sponsoring all the PCBs. They've got super low prices, fast shipping, and you can get a quote in minutes. They support a ton of different makers, so check them out next time you need anything manufactured. This is the smallest PCB that I've ever fully assembled, and actually my first time trying out stencils, so it was the perfect opportunity for me to pick up some new tools. I spent about an hour stenciling and meticulously placing components. I plugged in my new hot plate and it immediately fried. So I grabbed an iron instead. This worked really well until I needed to grab my board off of a hot iron and did not think ahead. Had no plan whatsoever.
These aren't quite big enough. I don't know how I'm going to pick this up.
The board slid off the iron, hit the table, and all the little tiny parts just flew everywhere.
Something? It's okay. It is useless, basically. I have to redo everything.
After that, I waited for the replacement hot plate, re-stenciled everything. This time I didn't do anything stupid. Everything soldered down in the right place. I hand soldered the top side, and everything was ready to test. After checking for shorts and not seeing any, I plugged in my battery for the first time. As soon as I plugged in the battery, I saw the 3.3 output go high. This should have idled off until the first press of a button. Looking closer at the schematic, it turns out I made a silly mistake. I routed the onboard push button as a short circuit. So as soon as the battery was plugged in, the on-off controller saw that short as a button press and enabled the 3.3 volt regulator. I desoldered the onboard push button to clear the short, and we'll just have to use the external header pins for now. But after doing this, the button circuit worked great. I could turn on and off power and see the button press interrupts being fired off. Next, I needed to test the battery charge circuit. I plugged in the micro USB charge cable to provide 5 volts and immediately saw the charge LED dimly light up, even though there was no battery connected. I was very confused since I literally copied Adafruit's design that they use on thousands of boards. At first I thought the diode O-ring circuit between the battery and the USB power was leaking current, but I removed that diode completely and I had the same issues. Since I thought this was a battery detection issue, I tried decreasing the bypass cap on the battery detect input, then I tried increasing it, removing it, nothing seemed to work. Then I got a little smarter and grabbed a spare feather board that I have lying around to run some tests with. I plugged in the micro USB cable first and the battery second, and guess what? I saw a dimly lit flashing charge LED. Turns out if you plug the battery first, then the micro USB cable, everything works as expected. I'm really happy with this first run. It's super compact and extremely functional. Honestly, I'm probably going to use this in all my future projects, and I've already got some cool ideas to experiment with, like tying a GPIO pin to the input of the button and having a microcontroller turn itself off. So make sure to subscribe if you want to see all the future projects I'm going to do, and if you haven't seen my e-kayak build, check that out.